In this presentation, I want to talk to you about land surveying. According to the Merriam-Webster's dictionary, surveying is a branch of applied mathematics that is concerned with determining the area of any portion of the Earth's surface, the lengths and directions of the boundary lines, and the contour of the surface, and accurately delineating them on paper. According to the publication Definitions of Surveying and Related Terms, a definition of a survey is to inspect or investigate something in order to determine its state or condition, and surveying as the actual making of a survey and the recording and or delineation of dimensions and details for subsequent use. At its core, surveying is a profession tied to the accurate location of property boundaries. The following are just a few of the most famous surveyors from history. George Washington, who was a surveyor general in Virginia in 1749. Thomas Jefferson, who was a county surveyor for Albemarle County, Virginia in 1773. Lewis and Clark, who led an expedition to explore and survey the West. Daniel Boone, who resolved Kentucky's land disputes. And Abraham Lincoln, who was a surveyor in Illinois when elected as a state legislature. Land surveying is the science of determining the relative positions of points on the Earth's surface. Land surveying is a wide area of study with many different types and methods employed by surveyors. There are two categories of land surveys that require different surveying methods: geodetic surveys and plane surveys. A geodetic survey is based on the true shape of the Earth. Geodetic surveys take into account the true size, shape, and gravity fields of the Earth. The true shape of the Earth is not a sphere, but an irregular ellipsoid shape. Many models of the true shape of the Earth exist. One model, the geoid, is a model of the assumed mean sea level, which is dependent on the gravitational forces around the world. The Western Hemisphere geoid is shown in the computer-generated model shown to the right. The yellow and orange areas are areas that are further from the center of the Earth than the blue areas. Geoid surveys use the geoid or another similar shaped model as a basis. These surveys are performed with great precision and are used to establish highly accurate control networks that provide points of known position throughout the U.S. and the world. Plane surveying is the survey in which the Earth's surface is assumed to be plane or flat, and the curvature of the Earth is ignored. Plane surveys extend only over small areas, and the lines connecting any 2 points on the surface of the Earth are treated as straight lines, and the angles between such lines are taken as plane angles. Plane surveys are more common than geodetic surveys. Plane surveys are precise enough for small-scale surveys in a limited area, such as a construction site. They are used to determine legal boundaries, construction surveys, and small area topographic or control surveys. This image shows the difference between a geodetic survey and a plane survey. In a geodetic survey, the geoid is taken as the datum. Lines that indicate level surfaces are actually moving with a smooth wave-like motion with the strength of the gravitational field. In a plane survey, the curvature of the Earth is considered flat, and the lines of equal elevation are assumed to be horizontal planes. In this class, we focus primarily on plane surveys. Here are some of the types of surveys that we will cover in this presentation: control surveys, topographic surveys, property surveys, site surveys, and construction surveys. Control surveys are used to establish precise horizontal and vertical, or the latitude and longitude and/or elevation of reference points that can be used for other types of surveys. The image here is published in the Seminole County Geodetic Control Points document from 2006, which provides a description of the location of each control point in addition to the latitude, longitude, and/or elevation. These control points can then be used as a basis for topographic, construction, or other surveys. The photos to the right show survey crew members setting survey marks during control surveys in Alaska. The black and white image was taken near White Pass, Alaska in 1936. The color photo is a more recent shot of a crew member mixing cement to set a mark in a rock in southeast Alaska. A topographic survey gathers data on the location of natural and man-made features, contours, and ground elevation to create a topographic map. This is an example of a topographic map for the area surrounding Stowe, Vermont. The contour lines indicate lines of constant elevation. A property survey establishes property or boundary lines for a lot or property and is used to create a plat. This is an example of a recorded plat created from a property survey near Mount Pleasant, South Carolina. The property lines are located using a length and a bearing angle. A site survey is a combination of a property survey and a topographic survey. Site surveys sometimes require a construction permit. This site plan shows both property lines and contours from a topographic survey. A construction survey locates points and elevations that can be used to establish correct locations and elevations for engineering and architectural projects. Examples of construction surveys include staking a line and grade for a foundation, a fence, or a road. In the picture below, the string lines were laid out based on a construction survey. Notice the surveying equipment to the right in the picture were used to ensure that the foundations are poured to the correct elevation. There are many other types of surveying employed for different purposes that use different techniques. The following are just a few of the other types of surveys: bathymetric surveys, deformation surveys, foundation surveys, geological surveys, and hydrographic surveys. A bathymetric survey will map the bed of an ocean, lake, river, or other body of water. Bathymetric surveys are used to measure the depth below sea level at certain points, whereas hypsometry surveys measures the height of the land above sea level. The depth measurement is likely to be carried out with the use of sound measuring such as sonar, and global positioning system, also known as GPS, will measure its position on the Earth's surface. Here is an example of a bathymetric survey. Deformation surveys are used to check for and measure change. They use geodetic measuring devices, geotechnical measuring devices, and other techniques such as radar measuring devices. Deformation can apply to dams, roads, mines, settlements, or volcanoes, and these can all be measured with this type of survey. Laser scanning is one method which can achieve an accurate measurement of deformation. These two pictures are examples of deformation surveys. A foundation survey is carried out to collect the positional data of construction foundations. These surveys are used to assess whether foundations have been laid at the planned depth and location. Hydrographic surveys map the coastline and seabed and are used in navigation and engineering. Here are a common set of reference points for all surveys. Horizontal datum, which is a collection of points of a known latitude and longitude. Vertical datum, which is a collection of points of a known elevation. A benchmark, which is a permanent mark that establishes a point of known elevation. You can search for information on datum reference points by referring to the National Geodetic Survey Data Explorer's National Geodetic Survey, which can be found at this link. The map you are about to see shows an area of a future project that will be located in Noblesville, Indiana. The red points are datum reference points. This map shows the datum reference points from the NGS Survey Control Map. All of the information about a datum point is available on a data sheet. The example you are about to see is from a point of horizontal and vertical control near a site in Noblesville, Indiana. The horizontal coordinates, the latitude and longitude, are highlighted in blue. The vertical height above mean sea level is highlighted in yellow. This is an example of a data sheet. In early times, survey lengths were frequently recorded using units of chains and lengths as measured with a metal chain, often referred to as a surveyor's chain. All optical equipment requires a visual line of sight. A level measures vertical differences in elevation. A theodolite measures vertical and horizontal angles. A total station is an electronic optical surveying instrument that combines a theodolite and an electronic distance meter to measure distances. These two images are examples of a theodolite and total station. An automatic level is commonly used on building sites because it is easy to set up and use. An internal compensator can automatically level the instrument. It can measure difference in elevation between the line of sight and a point. Other equipment often used in conventional optical surveys are a leveling rod, a tripod, a professional tape measure, and a field book. The leveling rod is used to measure vertical distances with optical equipment and looks like an extra long measuring stick. The tripod supports the surveying instrument. The professional tape measure is used to measure distances. The field book is used to record the measurements and observations taken during a survey. The images shown are examples of a leveling rod, tripod, professional tape measure, and a field book. The Global Positioning System, also known as GPS, is a global navigation satellite that can be used for surveying as well as navigation. The GPS system is a free-to-access system developed by the United States Department of Defense. It consists of a constellation of many satellites that orbit the Earth, each broadcasting a unique radio signal. GPS receivers intercept several satellite signals in order to determine the distance to each satellite based on the time it takes the signal to reach the receiver. The location of the receiver on Earth can be determined from as few as 3 satellite signals. Multiple satellites are always accessible from any point on Earth at any time. As the satellites orbit and the Earth spins, the number of visible satellites from a location changes. These images are examples of GPS technology. Some recreational GPS navigation units only calculate horizontal position, latitude and longitude, and superimpose the location on a map image. These units do not need a high degree of accuracy and may calculate location to within a few meters, close enough to determine which road you are on. Other handheld GPS receivers provide both horizontal and vertical position in terms of latitude, longitude, and elevation. The accuracy varies with the unit. Professional-grade GPS surveying equipment provides a much higher level of accuracy than the lower-cost recreational units. It calculates both horizontal and vertical position to a high degree of accuracy. Let's begin by looking at the various parts of an auto level. Before using the auto level, the instrument should be leveled so that when the instrument is rotated, the line of sight defines a horizontal plane. The leveling screws allow the surveyor to adjust the alignment of the instrument to provide a horizontal line of sight. If properly calibrated, the instrument will be level when the bubble in the bullseye level is within the circle. The mirror will reflect the bullseye level when viewing from the eyepiece height. The sight can be used to roughly align the telescope with the rod position. Rotation of the horizontal tangent knob results in a fine horizontal adjustment. When looking through the telescope, it will slowly adjust the view left to right. The horizontal angle rotation ring is used to approximate horizontal angles. Rotating the diopter adjustment ring, which surrounds the eyepiece, can sharpen the crosshairs when viewed through the eyepiece. Now, let's talk about reading the rod. Examine your rod to determine the increments used. On this rod, the red numbers indicate whole feet, and they actually measure a true 12 inches. Each foot is broken up into 10 number divisions. The black numbers indicate tenths of feet. Each tenth is further divided into 10 increments, which are indicated by the edges of the hatch marks. You will have to get used to counting edges of lines instead of the lines themselves. The tenths of feet and measurements that end in 5/100ths of feet are indicated by the long edge of a beveled hatch mark. This is a similar view you'd see looking through a telescope. You'd see the horizontal crosshair, the vertical crosshair, and the stadia hairs. What measurement does the horizontal crosshair indicate? The answer is 5.25 feet. This means that the line of sight of the instrument is at 5.25 feet above the point on which the rod rests. Notice that the horizontal crosshair is located at 5, then 0.2, and then 5. That's how we get 5.25 feet. It's at the bottom of the hash mark. If it were above this hash mark, it would have read 5.26 feet. The bottom of these hash marks are odd numbers and the top are even. You will notice that the stadia hairs can also be read. What is the upper stadia reading? The answer is 5.3 feet. When the crosshair or stadia readings fall within the white or black areas of the rod between the hash marks, choose the closest edge. What is the lower stadia reading? The answer is 5.2 feet. Now, estimate the distance from the rod to the instrument. This is just an estimated distance. Rod intercept is the difference between stadia readings. We subtract the upper stadia from the lower stadia. Now, take the rod intercept and multiply it by the stadia multiplier. The stadia multiplier typically equals 100. The stadia multiplier will be indicated inside the instrument case or in the instructional manual. Notice the rod intercept of 0.1 feet. Again, using the stadia readings, we can estimate the distance between the instrument and the rod. We calculated the rod intercept by subtracting the lower stadia reading from the upper stadia reading. Then we multiplied the rod intercept by the stadia multiplier, which is usually 100. To calculate the distance between the rod and the instrument, multiply the rod intercept by the stadia multiplier. Therefore, we would multiply 0.1 feet times 100, which would give us a distance of 10 feet. Let's practice reading the rod again. What measurement does the horizontal crosshair indicate? The answer would be 5.06 feet. What is the upper stadia reading? The answer would be 5.13 feet. What is the lower stadia reading? The answer would be 4.99 feet. Estimate the distance between the instrument and the rod using the stadia readings. What is the rod intercept? To calculate the rod intercept, we would subtract the lower stadia from the upper stadia. Therefore, we would subtract 4.99 feet from 5.13 feet, and we would get a rod intercept of 0.14 feet. What is the approximate distance? To calculate the distance, we would multiply the rod intercept times the stadia multiplier. Therefore, we would multiply 0.14 feet times 100, and that would give us a distance of 14 feet. Differential leveling is the establishment of differences in elevation between two or more points with respect to a datum. If you start with a point of known elevation, such as a benchmark, you can determine the elevation of another point using differential leveling. Let's use differential leveling to determine the elevation of 3 points, A, B, and C, using the known elevation of a benchmark, which is at an elevation of 350 feet. Land surveys record their measurements and observations in a field book. The notes include all the measurements taken and, depending on the type of survey performed, a sketch. The record of measurements and observations are often called field notes. Reproduce the sketch provided to you in this presentation of the plan view of a survey in your field book, which would be your engineering notebook. Sketch this plan view of a survey in your field book, which would be your engineering notebook. To find the elevation of an unknown point, you must start with a point of known elevation, such as a benchmark or another point of reference. Here the benchmark elevation is 350 feet. The rod person places the rod on the benchmark or point of reference, and the instrument person uses the instrument to read the rod. The rod reading is called a back sight. A back sight is always a sight back to a point of known elevation. In this case, the back sight reading is 7.59 feet, which means that the view through the telescope at the horizontal crosshair is at 7.59 feet above the benchmark elevation. We call the elevation of this line of sight the height of instrument. To find the height of instrument elevation, add the back sight to the benchmark elevation. In this case, the height of instrument is 350 feet plus 7.59 feet, or 357.59 feet. This is the distance from the datum to the line of sight of the instrument. In the table on the field notes, start with the point of known elevation. Always include zeros to show the precision of the information or measurement. In this case, we know the elevation to the hundredths place. Use zeros to indicate this. Record the back sight. The rod is incremented to hundredths of a foot. Find the height of instrument by adding the back sight to the known elevation. Note that the plus in the back sight column indicates that a back sight is always added to the elevation. Note that other information can also be recorded, including stadia readings, distance, and the horizontal angle between points. Record the stadia readings so that we can estimate distances. What is the estimated distance between the instrument and the rod using the stadia readings? First, we need to calculate the rod intercept. We calculate the rod intercept by subtracting the lower stadia from the upper stadia. Therefore, we would subtract 7.33 feet from 7.85 feet, and we would get a rod intercept of 0.52 feet. Now we're able to solve for the distance. To calculate the distance, we multiply the rod intercept by the stadia multiplier. Therefore, we would multiply 0.52 feet times 100, and that would give us a distance of 52 feet. It is important to note that at this point you do not move the tripod after you take a back sight until you have first taken a foresight. The rod person now moves to the point of interest and places the rod on the point of an unknown elevation. The instrument man uses the instrument to read the rod. This rod reading is called a foresight. A foresight is always a sight to a point of unknown elevation. In this case, the foresight reading is 2.36 feet, which means that the view through the telescope looking at the horizontal crosshair is at 2.36 feet above the point of interest. The elevation of the point of interest can be calculated by subtracting the foresight reading, which is 2.36 feet, from the height of instrument, which is 357.59 feet. Now, let's identify the elevation at this point by subtracting the foresight from the height of instrument. Therefore, we would subtract 2.36 feet from 357.59 feet. In this case, the elevation of the point of interest is 355.23 feet. Because you know the elevation of the benchmark, you will not take a foresight to that location. Place an X in the foresight column to ensure that you do not record a reading here. Record the point designation or name for the point of interest. Here we will call the location Point A or PTA. However, this could be a description such as a rock, building corner, top of curb, or some other permanent feature. Record the foresight in the Point A row. Now record the elevation of Point A next to the foresight. Notice the minus in the foresight column heading. A foresight is always subtracted from the elevation of the height of instrument, which is shown in the row above. Record the upper and lower stadia readings. Estimate the distance from the instrument to Point A. First, we need to calculate the rod intercept. To calculate the rod intercept, we subtract the lower stadia from the upper stadia. Therefore, we would subtract 2.19 feet from 2.54 feet and get a rod intercept of 0.35 feet. Now we can calculate the distance. To calculate the distance, we multiply the rod intercept by the stadia multiplier. Therefore, we would multiply 0.35 feet times 100 and get a distance of 35 feet. In review, we started with a known elevation at the benchmark. We then added the backsight to the benchmark elevation to obtain the height of instrument. We then subtracted the foresight to the point of interest from the height of instrument to obtain the elevation of the new point. If additional elevations are needed at points that are clearly visible from the location of the instrument, you may leave the instrument in place and move the rod to the other points of interest. Because you are not moving the instrument, the height of instrument will remain the same. These field notes show the progression of taking additional foresights to points of unknown elevations and calculating the elevations of these points. If the approximate distances are needed, don't forget to take the stadia readings while taking the foresight or backsight readings.